Right, here we go. So today's session is all about tackling some of the real challenges in the CAM world and showing you how SolidCAM can make a big difference, especially with powerful tools like iMachining and AFRM. We will also be in touch on how important CAD-CAM integration is in streamlining your workflow and cutting down those frustrating inefficiency. So our goal today is to keep this session practical, informative, and worth your time. And of course, we will make sure there's room for your questions at the end. So during this presentation, if you have any doubt, please feel free to drop it in the Q&A section, which you can see at the top of this Teams meeting toolbar, and we will make sure to address them one by one towards the end of this webinar. And also, under the same Q&A sections, we'll be sharing some links that could direct you to your next action plan after this webinar, so stay tuned. So without further ado, let's get started and dive into the key challenges we are all facing in the CAM space, and more importantly, how we can solve them. Zhongting, if you don't mind, can you help me to go back to the previous slide? Yep. So basically over here, this will be a brief agenda of what we're going to cover today. So we'll do an introduction to our company. Then we'll cover some of the industry challenges in the CAM business based on our engagement with the customer. And why is it important to have these seamless CAD-CAM integrations? And then we'll delve into the real content of this webinar, an overview of SolidCAM 2.5D, which give you all the basic capabilities such as drilling, milling, pocketing, profiling. And then we'll touch on one of the most patented and advanced technology in SolidCAM, namely SolidCAM iMachining. And lastly, we'll be taking a short stop at SolidCAM AFRM, Automatic Feature Recognition Module. Yep. Next. Right. So a short introduction about our company. We, CADVision System, we are the preferred partner of SolidWorks and SolidCAM in both Malaysia and Singapore. And our specialization not just lies within SolidCAM, we also have our footprint on CAD, computer-aided design, such as your drawing tools, on CAM, as you all of you may have heard of, may have known about this. CAE, computer-aided engineering, such as simulations or analysis tool. We are also specialized in product data management, manufacturing execution system, and enterprise resource planning. So all solutions and technology software that is relevant to these sections, we could be one of the partners that can help you in this area. Next slides. Yep. So over here, we have successfully gathered some industry challenges based on our past interaction with our customer, specifically in the context of CAM business. So in CAM business, a lot of us are talking about manufacturing. So high manufacturing cost is definitely one of the most primary challenges that is faced by a lot of the players in this battlefield. So manufacturing costs, this could be from prolonged machine cycle time. This could be excessive tool wear. This could be coming from high scrap rates. All this component, eventually it will drive up the part cost and reduce profitability. And second challenges that are also commonly experienced by this industry is basically inefficiency in handling design changes. So a lot of us today here, probably you have your own product, or maybe most of us are just contract manufacturing. So when we receive this files from customer, we have done our programming on it, but suddenly there is a change in the design. So how to manage all these design changes without having too much of a manual work, this is also one of the particular challenge in the industry. And thirdly is basically the inability to machine complex parts reliably. So a lot of the machining shop floor today, they are still relying on the programmer to program directly on the machine. So this could work for those more simple kind of like 3D machining. But when it comes to say like 4-axis, 5-axis, you want to have some mill turn, or even the most complex Swiss type machining, that's pretty much impossible to machine directly on the machine. And fourth, we should also admit that it is very difficult in today's industry to get a certified CAM programmers. And what makes it more difficult is basically the CAM system is getting more complex, and this significantly slow down the onboarding process for all this CAM programmer, which is already a rare resource. And last but not least, underutilization of CNC machines. So during our visit, we have seen that a lot of customers, they have enough orders, but the machines are left unrun because sometimes they need to do some programming on the machines. So they need to reserve that machines for some offline programming. Sometimes it's just that they do not have, say, the right tools or the right knowledge to program on that particular machines. Next slides. So next, why SolidCAM? So there are plenty of tools available in the market. Those CAM software, you can name it like Mastercam, Hypermill, but why SolidCAM? So today we are going from the angle of a SolidWorks user. So SolidCAM is not just compatible with SolidWorks, it's basically embedded. So unlike many CAM tools that link or import from SolidWorks, SolidCAM run entirely within the SolidWorks interface as a native tab. So as a SolidWorks user, SolidCAM boosts your programming efficiency by eliminating file transfer, file conversions, or file exports. So the CAM and CAD data basically operate on the same model in real time. So next, it's all about full parametric associativity. So when a designer makes changes to a SolidWorks part, this could be a hole size, this could be a geometry, this could be a features. SolidWorks CAM will automatically update the machining operations and rebuild the machining toolpath for you. CAM operations are tied to the SolidWorks feature tree, not just the geometry itself. So this is deeper than just simple geometry relinking. So in addition to this, SolidCAM also able to recognize native SolidWorks feature like bosses, pockets, holes, and pattern. And it can also select similar geometry and group them together, which we will see in the AFRM sections. So this will significantly make the programming faster and more intelligent. And last but not least, SolidCAM inherits SolidWorks UI and UX convention, such as the ribbon, the right-click menu, the graphics controls, the shortcuts, so making it very easy to onboard existing SolidWorks user. Next up. All right, so now we'll get into the actual content of today's webinar. So we have covered what are the common challenges in the CAM industry. We have covered why SolidCAM is particularly great, and especially if you're a SolidWorks user. And now let's take a look into the SolidCAM portfolio. So in the center, you'll be seeing that there's two bricks, one for SolidWorks and 1.2.5 axis milling. So SolidWorks, as all of us know, is a design software. SolidCAM 2.5D built on top of SolidWorks using the same UI, and this 2.5D basically serve as the basic building blocks for all the SolidCAM module. So in 2.5D, which we'll cover in the later section, you'll be seeing the capabilities such as doing pocketing, profiling, face milling, drilling, different level machining, you name it. So on top of it, on the left side, we'll start with some HS module, which is the acronym for high speed. We have 3D milling, high speed surfacing, HSS. We have HSM, high speed machining. We have HSR, high speed roughing. So basically, this gives you the ability to perform all this conventional surfacing, machining, and roughing operations in a high speed module. And slightly moving clockwise, we have iMachining 2D and 3D. This is basically one of the patented technologies in SolidCAM that allows you to create more, more advanced toolpath, namely the spiral morphing toolpath. And on the right side, SolidCAM not just stop at 3 axis, it also extends its capability to 4, 5 axis. And you can also do machine simulation if your intention is to check whether is there any collision between the model that you're going to machine and the machine boundary itself. And moving down, other than just all the milling capabilities, SolidCAM also venture into the areas of turning. And of course, you have milling, you have turning. Then the next thing that SolidCAM can offer to you is basically the advanced Milton. They include like multi-turret, multi-spindle synchronization. And some of you might have gone into this business of machining small, intricate component. For example, like maybe those gears in your watch, maybe those component within a specific car control module. So basically, this will require a more intricate machining type, which is known as Swiss type. And further down, we have AFRM, which is also one of the topic today, is basically automatic feature recognition module. Because sometimes, occasionally in our model, there are some repeating features. Probably I have 100 holes. So how can I capture all this hole all together and apply one similar machining strategy to them by having different level of cut, different level of depth? That could be done using AFRM, which we'll also cover in today's webinar. And last but not least, on the bottom left corner, we have Solid Probe. Solid Probe basically is inspection on the go on the CNC machine. So basically, when you're trying to do some in-process machining and you want to ensure that whether this model is perfectly machined, is there any deviation? So instead of just taking it out from the CNC machine and put into a CMM or do some manual measurement, you can basically use Solid Probe to do the inspection routines on the CNC machine directly during this in-process machining. So I hope I have made this clear. So let's move on to the next one, SolidCAM 2.5D milling. So as explained just now, SolidCAM 2.5D milling serves as the framework for all the SolidCAM module. It's the building block. So what's so special about SolidCAM 2.5D? So first is basically feature-based machining. So SolidCAM automatically recognizes SolidWorks design features like holes, pockets, bosses to streamline your programming process. So you can have a single pocket or drill recognition operation to machine a group of pockets and holes on varying level and depth. And second, efficient and intuitive workflows. So in SolidCAM, what we're trying to advocate to our customer is that for every operation that you wish to create in SolidCAM, it comes with a simple wizard that can guide you through your creating operations like face milling, contouring, pocketing, drilling, engraving, and threading by first directing you to select the right geometry, then selecting the right tools, selecting the right strategies, and then you can simulate. So it's basically like a step-by-step guided wizard. And third, parametric updates made easy. So as mentioned in the previous slide, any changes in the upstream design process, specifically in SolidWorks, you change the feature, you change the dimension, you change the model size, all this will instantly update your SolidCAM machining operation and help to rebuild your toolpath without even require any human interventions. And stock and target definition from CAD. So why is this important? So basically, SolidCAM use your SolidWorks model to define for both your stock, which is your raw material, and your target, which is your finished model. No need for any external geometry. And the reason why this stock and target definition is important is basically SolidCAM will utilize these two and compare them at real time to calculate the rest material. It's basically those material that is left over from the previous machining operation. As SolidCAM dynamically compute all this remaining stock model after each machining operation, you can ensure that by the end of your CAM program, all your stock model, unnecessary stock model, has been removed to get your intended finished product. And last thing about SolidCAM 2.5D milling is the tool library and simulation. So in SolidCAM, you can basically treat it as a knowledge base for your CAM programming knowledge. So you can store all your predefined tools, you can store all your predefined machining strategies, you can store all your predefined machine parameters, all inside SolidWorks at SolidCAM, and also some of your templates, for example, like your tool table, your reporting templates. So, and with all these libraries and templates, on top of this, you can also run simulation and collision detection, all within the same environment. So I think I have said enough. So I'll pass back the floor to Zhangting to give you a dive into what SolidCAM 2.5D actually looks like within the SolidWorks environment.
Okay, thank you, Tanyang, for the great sharing sessions. So let's have a look at a walkthrough video of SolidCAM 2.5D. So as you already know, 2.5D offers various types of machining operations. And in these videos, we're going to see how we are to program a pocketing operations. So once you create a new pocketing operations, you can see a handy wizard will pop up for you to guide you on how to program your machining operation itself. And in here, you can specify the geometry you want to machines. And also, you can directly select the tools from your tool tables. So for this case, I'm going to use a end mill, a 12mm end mill to mill this pocket right here. And also, it will guide you to select the levels, the depth you want to machines. And you can see that we can directly choose the level based on our 3D CAD models. So we don't need to measure it by ourselves. We don't need to know the parameter. Even we don't know the parameter, we can directly choose on the CAD models. And in the technology tabs, it will guide you on those parameters you want to input. And on the left bottom corner of the wizards, you can see that there's a handy icon for you to tell you what parameters you are actually working on. And we will go ahead and set up our pocketing operations, like telling it what is the ramping strategy and what is the linking strategy, and go ahead and simulate it to check for any potential collisions and unwanted tool movements. So you can see that this pocketing operation is success. But after that, if you have anything you want to change within these operations, you can directly go back to these operations. For example, I want to change the step down. I don't want the tools to go too deep at the first time. So I will change my step down to 7, and you can see how easily it is able to recalculate the toolpath and give me a new toolpath. So we'll go ahead and see the simulations to check for any collisions, any unwanted movements. Okay, once we are satisfied with this, then what if we want to reuse these operations for another geometry? So we can directly save and copy, and it will read those parameters from the previous operations and brings to another operation. And in here, we can do some minor changing, such as what I'm doing now is changing the geometries, and also I'm changing the pocket level. So the upper level will be another level, and also I will change the pocket depth as well. So you can see how easily we are able to copy an operations we are satisfied with and use it on another pocket. So we don't need to change too much parameters and re-input those parameters again. So we'll go ahead, and after we input the parameters we want, we'll go ahead and save and calculate those two paths. And we can also check for the collision as well during the simulations. You can see, yep, the bottom pocket is the operation is success. So after that, what happened is I already done my roughings. So I want to do finishings using the same operation. So I can directly save and copy, and you can see now I'm able to choose the roughing operations I'm using. I am going to finish for. So I'm choosing the pocket number 1, and I will go ahead and remove the offsets because I want to do a finishings. And with this option right here, you can choose to only machine those rest material left by the previous operation. So after I choose this operation, you can see that I can specify the previous operations. So previously I use a 12mm, so I will just type in a 13mm end mill I'm going to use. So after I do those lead in and lead out, those linking strategies, and you will see the simulation in a while. So you can see that the tool only machine those rest material left by the first operations. So we are satisfied with this. So we go ahead and save and copy and go ahead and finish the pocket number 2. So I just change the operations that it is referenced to. So that is pocket number 2. Then I go ahead and change the technology to rest material and using the same parameters, remove those offsets, and I'll go ahead and simulate it again. So you can see that it is able to automatically compute those rest material left by the previous operations. So you don't need to, you can eliminate those air cuts in your machinings. And what if we want to rotate the part to another coordinates or another orientations? So we can also change the machine coordinate system, which is the orientations in SolidCAM context. So you can see here, I have several coordinates I have set up, and I want to machine the side of the 3D model right now. So I just go ahead and need to a similar flow with specific in SolidCAM software itself. So after we are done setting up those parameters, how we want to cut these parts, and we can go ahead and simulate it again. So you can see how it approach the pocket from the outside when the pocket is has an open area. So now we are going to machine another side, which is a true pocket right here. So I go ahead and select my geometry, my tools I'm going to use. So you can see here there's a tool table that Tanya mentioned just now. And also we'll go ahead and specify the level, the technologies, and also the ramping strategies. So after I save and calculate, I simulate it, I found out it is not what I wanted because we choose helical ramping strategies and there's no enough space for it to do a helical ramping. So we go ahead and change it to none. So we don't have any ramping strategy. So later on, you can see after we calculate the toolpath and we simulate it, the ML will go directly in the middle. But this is not what we wanted. So what other people typically do is we will pre-drill a hole in the middle of the ML for the ML to enter and then pocket it from the pre-drill hole. But we don't know which point the ML is going to enter, and we cannot sketch a point to specify the drill entrance point. So what we can do here is go ahead, we can select the drilling operations, and you can see here in the geometry tab, we can directly choose the entry point of the end mirror itself. So you can see here, yeah, drill for contour 4. So this is the end mirror entrance point. So we can directly choose this geometry and it will recognize the entrance point of the end mirror itself. So we go ahead and select our tool, and you can see after we specify those drilling depth, how we want to drill this part. Okay. And you can see that the drill actually come before the pocketing operation itself. So it will automatically arrange the drill before the pocket itself. And after that, you can go ahead and simulate the pocket operations. You can see that actually there's already a hole in the middle before the pocket operations. So the ML can enter from the middle. So once we are satisfied with this, then we can save the operations and exit, and we can generate G code based on this CAM program. So that's it for the walkthrough video of SolidCAM 2.5D. I will pass it back to Zhan Yang for the iMachining explanations.
Right. Thanks, Dongting. So probably you have already seen those 2.5D milling in other CAM software. It's nothing special. It's quite common, but there are also some challenges in all this conventional CNC program. So basically, in all this normal 2.5D, we are expecting something like a racetrack program. So probably you start with the outer layer, you machine the outer layer, and then you go in, step over maybe with a 5mm, then you machine the next layer. So it's still good, but there are some rooms that we can improve on all this conventional CNC program. So one of the biggest challenges in the traditional CNC programming is to figuring out the right speed and feeds so you can push your machine to its full potential without damaging the tools or risking failure. So the truth is, calculating the optimal cutting condition isn't simple. You will need to account for four major factors. The material being cut. This could include like cutting speed, your hardness, what's the maximum minimum step value. Second, the tool you are using. This could be what's the optimum length of the tools, how many flutes should I use, what should be the helix angle, how thick the chip should going to be, and what's the hardness of the tool itself. And third factor is basically the geometry. What is the depth of cut? If today I have a 20mm cut, should I go one straight to cut everything, or should I divide it into two steps operation or 4 steps? And last but not least, the last factor is machine. So what's the maximum speed and feed that my machine take in? What's the maximum power I can supply? What's the memory size that is allowable for my CAM program? So calculating all this parameter isn't simple, and a lot of time we are relying on the CAM expertise to do this. But you might be wondering whether my program is optimum or not. So each of this, it includes multiple variables. And most CAM systems today, they only consider a subset of this, which leads to incomplete inputs, and that means unreliable or overly conservative feed and speed, because we certainly don't want our tool to break, we certainly don't want to jeopardize our machine, so we tend to be safe. We tend to play at a relatively lower value, but you are not maximizing your machine. So another big limitations of the conventional CAM software is its reliance on the fixed step-over toolpath, which is, like I mentioned, the racetrack. So this create consistent tool engagement only in theory, but in practical, especially around the sharp corners or very tight curve, the tool will suddenly encounter significantly higher cutting forces because it tends to change angle. Maybe when today, if I'm cutting a sharp radius, only 30 or 40% of my tool is in engagement with the material. So this will create an unbalanced force and result in significant difference in cutting forces. And also, to avoid tool breakage or wear, operators forced to slow down the feed rate and relatively take a shallow cut, not because the whole part requires it, but just to handle those few high-stress areas. So this often results in a slower overall process and inefficient use of the cutter, since only a small portion of the tool cutting edge is engaged most of the time. And this not only hurts your productivity, it also shortens your tool life, it increases your machining costs, increase your machining time, and limits your ability to scale. So in next slide, we are going to see how iMachining can address all these challenges that I've mentioned here. So in the later part, Zhongting will show you how iMachining run in live action. But before we move into that, let me brief with you some of the iMachining patented technology so you can better appreciate the walkthrough later on. So the primary technology that is patented under iMachining, it's an intelligent toolpath. So later in the walkthrough video, you're going to see iMachining cutting, not in the conventional racetrack movement, but rather in a morphing spiral. So morphing spiral, basically to make it sounds more human, you can think of it like drawing circle gradually conforms to the geometry. So say today, if the geometry that I would like to cut is maybe in the shape of number 8. So if has like two circular movement. In between, there is some filleted radius. So basically, the cutting movement of the tools will be confirming this geometry rather than the old-fashioned racetrack toolpath. And second, good advancement under this iron machining toolpath is molding. So as you can see on the image here at the bottom right corner, basically if today I have two islands, I don't have to specify two operation, or I don't have to, because of getting one single operation, I reduce the diameter of the tool. Basically, I can use the intended tool diameter, and iron machining will automatically identify, oh, probably between these two islands, I cannot directly cut through. So I will be creating two cutting movement within one single operations. After I machine the first island, I will retract my tool to a safe distance, and I move to the second island and I start targeting that island. So this is what we call molding. And third great things about iron machining toolpath is basically air cut elimination. So just now during my previous slides, I did mention that SolidCAM utilizes SolidWorks to define stock and target material. And basically, the benefit of this, it will dynamically compute what's the remaining material that should be removed within this operation. And with that in mind, basically, SolidCAM will eliminate those unnecessary air cutting. Says today, if I just want to cut maybe slightly into a profile, I don't have to go through the whole model and then cut in layer by layer. Basically, my tool can just move to that particular feature and go in to do all the cutting. So this eliminates all the unnecessary air cuts. And last great thing about iron machining toolpath, it's smart repositioning. So it helps to position the cutting tool from one cut to another at a cut depth, only retract when necessary. So you won't be seeing the tool like keep on going down, going up, move to another position. It only goes up when there is a necessity, meaning maybe if it goes at the same level, it will cut through another unexpected, unintended part, then it will only retract. So next slide. Right, so that's about toolpath. But iron machining is not just excellent in toolpath. Basically, another very great advantage of iron machining is that it can help you to save your tool life up to 5 to 7 times, and that is statistically proven. And how iron machining do this is basically through variable cutting angles and feed. So unlike those traditional toolpath, iron machining intelligently keeps the cutting angle between optimal, minimum, and maximum value. And here where it gets really smart. It automatically adjusts the feed rate in real time to maintain a constant load on the spindle, even as the width of the cut change. So when the toolpath is narrowing for a smoother morphing, iron machining increase the feed rate to keep everything balanced, which you can see on the right side of the screen. If today the cutting angle is reduced, the feed rate goes up. If the cutting angle is maximized, the feed rate goes down. So at any point of time, the force that is experienced on the cutting tool or on the spindle is always constant. And this results in high-speed cutting, less stress on the tool, and reduced wear on your machine, all while maintaining incredible precision. Next. Right. So we have talked about how iron machining differentiates itself from the perspective of toolpath. We have talked about the constant tool force. And now another very good features for iron machining is basically technology wizard. And this could be especially useful for those fresh CAM programmer or maybe some experienced programmer. You might also be benefiting from this. So what you can see on the screen, this built-in wizard is completely takes the guesswork out of setting a machine parameter. So instead of you manually figuring out the value to be set, the wizard automatically calculates the optimal cutting condition based on your material, based on your tools, based on your fixture setup, or even the capabilities of your CNC machine. So it helps to synchronize everything. As you can see on the left picture, your feed rate, your spindle speed, your depth of cut, your cutting angle, and even your chip thickness, so that you are always running at the most efficient settings without overloading the tool or the machine. And here's the best part. It's built for real-world condition. So with the eye machining level slider, which you can see from the left picture at the top right corner, there is a machining level from 1 to 8. You can choose from the 8, which is the preset level, to match the stability of your setups. So level 1, basically this gives you the most conservative settings. This is ideal if you have a very old machine or maybe a less rigid setups or delicate toolings that you wish to protect. And level 8 basically push the envelope with maximum material removal rate. Basically, this means that the cycle time is lesser. You're removing material at a relatively largest amount and is high performance. And level 2 to level 7 offer a smooth, graduated steps in between, letting you fine-tune based on real-world experience. So on the right side, you can basically see how all this machining level affects the chip thickness. So if I go with 1, the chip thickness is relatively thin, and basically this the forces on the tool is relatively lower. If I go to 8, the opposite will happen. So instead of just like guessing, experimenting, and risking the tool breakage or inefficient cutting, technology wizards in SolidCAM eye machining do all the heavy lifting for you, giving you a safer, faster, and smarter machining right off the gates. So I believe right now you might have get excited to see this to run live in action. So I will let Zhong Ting to bring you to how it actually runs in the real environment. Back to you.
All right, thank you, Tanyang. So I'm going to show you guys walkthrough videos for SolidCAM eye machinings 2D and also 3D. So as you can see here, we are looking at SolidCAM eye machining 3D first. So just now we mentioned that we need the material properties, the machine's parameters. So this is where we can choose the material properties, and also this material database is linked with our SolidWorks database, material database. And after that, we have machine and material. Now we specify the geometries. So what is the geometry we want to cut? And after that, you have all these three things. We go to the tools. So you can specify what tool you want to use. And it is important for the system to know what is the tool materials and also what is the helix angles to calculate the feed rate later on. So after you see here, we choose the material we are using, the helix angle. After we save all this, we have all four of these, and the system directly tell you this is the part you're going to cut later. And this is the similar like 2.5D. We can specify the depth we want to cut, but it will automatically compute for you. Just in case you want to change it, you can change it later. And here comes the eye machining magics. This is the technology wizards by eye machinings. So based on those parameters we input just now, you can see that it automatically calculates the spin rate and the feed rate, the step over, the maximum step over, and also the minimums. So you can see that in fact we cannot change all this because this is automatically calculated based on your machine parameter, your material properties, and give you the most optimum cutting conditions. But you can see in the modified cutting conditions here, all this value is already calculated for you. So you can see the maximum cutting angle, the minimum cutting angles. And if you want to change it, you can change it at the cutting conditions, and it will automatically recalculate those spin rate, feed rate for use based on later on we will see how we can change it. And also you can see the ACP right now is in the green zone, so it means that there's less vibrations on your tools. So after we calculate the toolpath, you can see the toolpath is actually gradually conform to the geometry of the fillet on the corners. And we'll go ahead and simulate it. And pay attention to the simulation data on the left here. So you can see the feed rate and spin rate varies when the cutting angle changes during the machining operations. So you can see when the cutting angle change reduce, the feed rate will increase. So this is to ensure there's a constant tool force on your tool to minimize the tool breakage and also greatly prolong your tool life. And by varying the feed rate, you can eliminate those slow movements, like it can greatly reduce the machining times for this specific parts. So just now we say that iMachining will read those material database, the material properties from the material we choose. So what if today's your boss asks you to choose to change to another material? Your company is cutting another material, so we can go ahead and change it right here. So we can see we change to a harder material, so two-stage material. You can see how it affects those spin rate and feed rate. So after we change the material, it tells you, okay, this operations is affected by the material change. And when you go back to it, you can see in the technology wizards, the spin rate and fin rate has been reduced because this is a harder material and our tool is not that strong to cut this material. So it will reduce that those parameters to ensure that it doesn't break the tool easily. So we don't need a lot of CNC knowledge to guess or to get those parameters. We can use iMachining and it will be easy for you to get on board on this to get a first time cut success. So you can see that I can use a turbo mode to increase the power and my the spindle power. So you can see that now I'm operating the motor at 7.5 kilowatt. Then you can go ahead and see my spin rate and feed rate has been changed because I switched on the turbo mode just now. And you can see the ACP is also in the green zone, so we can go ahead and try to simulate it and see any unwanted movements. So after we calculate the tool path, we can ask the program to give us the machining time first. Okay, so you can see this part only takes 3 minutes to cut. So we will compare it to a conventional cutting. So we go ahead and drag a template. So this is a pocket roughing. So we just drag the template. So you can see this is the typical racetrack toolpath we are going to generate. So you can see the difference between iMachining toolpath and also a conventional toolpath. Now, after I input those parameters I want to use and go ahead and calculate the machining time, you can see that it takes around 17 minutes to cut that pocket itself. So you can see around 5 times faster than conventional cuttings by using iMachining. And also your tool life will be greatly prolonged. Now let's go ahead and see iMachine 3D. So iMachine 3D is different from iMachine 2D because you can directly choose the targets you want to achieve, which is the final model you want to achieve, and it will automatically generate the tool path to cut the whole 3D model itself. So you don't need to do like iMachine 2D just now, you need to choose a pocket, anything. So we go ahead and select the machine we want to use first, right? And the material. After we have all this, we can go ahead and add our iMachine 3D operations. So you can see here in the geometry tab, we can directly choose the 3D model as our target and go ahead and select our tool. So we use a M mill for this case, 60 millimeter M mill. So we need to input those parameters we want to use. Okay, go ahead and specify the tool holder. After you are satisfied with all this, then you can go to the technology widget to check out the machining parameters. So the spin rate and feed rate has been automatically calculated for you. And we can check that our motor is operating at 10.4 kilowatt. So we don't want that. So we can go ahead and pick it and modify it to, for example, 7 we want to use like just now. All right. So after we change it, you can see the spin rate and feed rate has been changed. And also one interesting features in iMachine 3D is the scalloping strategy to rough those slanted surface. So later on when in the simulations, you can see what it means. So you can see that the toolpath has been generated to machine the whole 3D models. And we go ahead and simulate it using our machine simulations. Go ahead and simulate it. Oh, this solid verify. So you can see that is machining the whole 3D models because we are using iMachine 3D, and you can see during the slanted surface is actually doing a scalloping to ensure that the maximum material removal rate during the roughing operations. So this can greatly reduce the machining time at the subsequent operations where you want to do finishing on the slanted surface, right? So these whole operations, later on you can see how long it takes to cut this whole part at the simulation data right on the left. So you can see this whole operation only takes like 3 minutes 15 seconds, which is very fast for wrapping operations. And most of the material has been removed during this operation itself. All right, that's the end of iMachine 2D and 3D walkthrough videos. I will pass it back for Zhanyang to explain on the AFRM.
Right. Yep. So basically, for today, we have covered on the basic module, SolidCAM 2.5D. We have also touched on one of the advanced technology enhancement in SolidCAM, which is the SolidCAM iMachining. And the last part of today's webinar, we are going to briefly touch on another very interesting module called SolidCAM AFRM, which stands for Automatic Feature Recognition Module. So as suggested by its name, SolidCAM AFRM, it helps to capture similar features so that the user can apply one uniform strategy to all these features, but still maintaining the flexibility to decide on that says the depth of cut, the tool to be used, or maybe some minor tune on each group specification. So how AFRM work is that SolidCAM basically automatically recognize all your pockets. So the pockets can be open, can be closed, can be blind, can be true pockets, on your sharp edges where a chamfer can be applied, all your drills and holes, and also complex holes on the solid model, which you create all these holes using SolidWorks Hole Wizard. Says maybe this is a counter bore hole, this is a counter sun hole, this is a true hole, by applying automatic grouping through user-defined criteria. So say, for example, on the bottom left corner under advanced drill, maybe over here I have around 50 holes, but I want to apply this strategy to those holes that is below diameter of 20 millimeters. I can do that. Then for between 21 to 50 millimeters, I want to apply another strategies. So that could be well achievable. So standard machining strategies will then be applied to all this group geometry. Then you can combine with like multi-level and multi-depth cut. And this can happen to all the features that has been highlighted on the screen. Your pockets, your chamfer or deburring, your advanced drilling, or maybe your hole wizard. So without further ado, Zhong Ting let walk us through the live actions.
Okay. So let's have a look at the live actions of SolidCAM AFRM, Automatic Feature Recognition modules. So let's start. So you can see on these CAD models we want to machine. So you can see there's a different type of pockets. We have open pocket, and also we have pocket of different depth from the top until this island right here. And also inside the part itself, also we have another pocket. And inside that pocket, we have different pocket also. So from this, from the top, and also have a small step right there is also considered a pocket. So typically, we will need to specify a lot of pocketing operations of different depths and selecting different geometry using a conventional 2.5D. But using our pocket recognition modules, you can directly select. You can see that there's a similar interface with pocketing operations, but in the geometry itself, so you can directly choose like you can see there's 3 different type of selection modes. So we can see on the left here, we have a solid body, which is you select the solid body and recognize all the pocket inside these solid bodies. And we have face and also a true pocket change, which is a true pocket itself. And how do we filter out those small holes? So for example, this hole is considered a pocket. And what about those small holes right here? Do we consider it as a pocket or a hole? We want to use a drilling for this case, right? So how do we eliminate all this from recognizing as a pocket? So we can see here on the left here, we have a circular pocket diameter filter. So we can apply those filters to filter out the hole that is too small to be considered as a pocket itself, so that we don't do any machinings to those small hole because we want to do a drilling operations. So we go ahead and check it on our 3D models. So we can see this is a 20 millimeters hole. So we will go ahead and say anything below 90 meters, we don't consider it as a pocket. So our selection modes, we will use a solid bodies. So you can see we directly click on the solid bodies and it automatically recognizes those faces within this solid bodies itself. So you can click on all the faces recognized by the pocket recognition modules. And this is a true pocket change, which is recognized by the AFRM module itself also. And after you have all these pocket recognized already, then you can go ahead and do the same workflow like pocketing operations, which is selecting tools. And you can see in the levels also. So typically we will need to specify the depth of the cut. So in here we can see there's no depth of the cut. We can only choose the upper level because there's different type of pocket within these solid bodies. So it will automatically compute this depth and pass it back to these operations. So we cannot specify how deep we want our cut to be because it is automatically recognized from the AFRM module already. And you can see here we can specify those technology we want to use for an open pocket. So, and after we are satisfied with those parameters we enter, we can go ahead and save and calculate and simulate it to see if the result is what we wanted. So you can see this during these simulations, the pocket has been successfully milled in one single operation. So typically we will need multiple operations to do this, but using AFRM module, we only need to specify one operations and it will pocket the whole body for us. So this greatly saves your programming time. And for the hole recognition as well, you can see in these solid models, there's different type of hole, or small holes, big holes, or a chamfer hole, or drill holes. So you can see here, there's also a similar filter like pocket recognitions. We can filter out those big holes so that we don't want to use because we don't want to use a drilling operations to do a big hole, right? So we can filter out. So after we filter out, we can press one button to find all the holes within these solid models. So you can see on the left side, left bottom corner right here, there's a hole tree, and they group all these holes by their shapes, their diameter, their depth, and we can do different operation based on the groups we want. So for example, I want to remove the shape number 1 hole. So we just remove it from the operations. Okay, go ahead and preview it to find all the hole first. So how all these hole is located in your 3D model. So imagine you have a big 3D CAD model, a 3D model, big model with different type of holes. So you can easily find them using this. So go ahead and remove this hole because we don't want to do these operations for this type of hole. And go ahead, after we are satisfied with the hole that is found by the system, we can go ahead and specify those drilling technologies we want, the tool we want to use, and simulate it. And that's it for our SolidCAM AFRM walkthrough video. And here comes the end of our SolidCAM webinar. So if you have any questions, feel free to post your questions in our Q&A chat box, and we will address it one by one during the end of these sessions. And also, we have something to announce that our upcoming events will be on July 16th, which we will cover HSM module, HSR, and all HSS modules. So you can, if you are interested in those high-speed modules and how it achieve the machining operations for 3D cut compared to 2.5D, then you feel free to register your attendance using the link posted just now. And also, after these two events, if you are interested to join our hands-on test drive, we have a workshop on July 23rd as well. So feel free to register using the link we sent just now. And also, our CAM solutions and CAD solutions are the pre-approved solutions under Productivity Solution Grant, which is our PSG. So for customers that are entitled for PSG grant, they are entitled to up to 50% discount on the CAD CAM packages. So you can check your eligibility in our websites or using the link we posted just now. And also, we have a survey form later on. You can fill in your interest, and our account managers will reach out to you for more information about these grants. And on the right here, you can scan this QR code to give us any feedbacks, what you would like to see in the futures, what you want to tell us, anything you can give us feedback. Yeah, thank you everyone. So we'll go ahead and check out is there any question posted by you guys?
Hello, everyone. So thank you for joining us in today's webinar. So as mentioned by Zhongting, kindly help us to fill up the survey form and by either scanning the QR code on the right side of the slides, or you can also refer to the link that we have attached in the Q&A sections. So as of now, we do not have any inquiries under the Q&A segment. We will keep this webinar running for another 5 minutes before we wrap this session up. Yep, thank you for attendance today. All right, that will be what we intend to share today. And thank you for your time. I hope you enjoyed these sessions. Have a good day. We will be closing this meeting soon.
Thank you everyone for joining.